Thank you. So, yes, Chris de Vreeze now with a presentation about Scala and the yaidom library.
Yaidom, yeah. Okay.
Thank you.
Hi, I'm Chris de Vreeze from EBPI, a firm in the Netherlands where we do a lot of XML processing. And XML is a very XML-intensive standard. And the topic of the talk is yet another XML library written in Scala, which helps us processing XML and validating XML. So first, I'll briefly try to answer what yaidom is, and then we get to the use case, to the sample data, XML data. Then we get to some higher order functions of the Scala Collections API. After that, some higher order functions of the yaidom query API. And after that, we've seen enough of yaidom to get to the second part, which is more interesting, in which we write some XML validations as XML validations using yaidom. So what is yaidom? It's yet another XML query language, API. It leverages the Scala language and the Scala Collections API. Now the Scala Collections API is very nice to use. It's sort of a universal query API. And it's very nice if you can leverage that. Now this is not the only Scala XML library. There's of course the standard Scala XML library. That was the topic of talk last year by William Narmontas. This is another library, and we'll get shortly to why there is yet another Scala XML library. The library first, at a low level, defines some core concepts for expanded names, qualified names, in-scope namespaces, etc. On top of that, it defines some namespace support independent of the actual element implementations. Then the query API of yaidom is built on top of its namespace support. And the same query API of yaidom is offered by multiple element implementations. And that is something that is a difference with the standard Scala XML library. You could even easily add your own custom element implementations, for instance wrappers around existing DOM trees of libraries such as yaidom or XOM. And even type-safe custom element implementations for specific XML dialects. But I don't have time to turn to that. Okay, so the use case is XML. And XML is a financial reporting language, like I said. It's very XML intensive. Here we have a small example. The root element is XML in the XML instance namespace. So this is a report in the XML standard. We see in yellow two top-level facts. The equity fact and the entity address presentation fact. The equity fact is a so-called item fact. It has no child facts. The entity address presentation is a tuple fact, and it does have child facts. Now the equity fact can be interpreted as follows. We see a value of 95,000, but what is the unit? Well, we see a unit ref to the unit in green, so it says euro. So we know the equity is 95,000 euros. But what is the period and what is the identifier of the business? Well, we see a context ref to the context in red, and it says that the period is 2014, and the identifier of the company is the number that you see there. So this is a very small but still functional example of an XML instance. Okay. Now let's get to Scala Collections. Last year, in a talk of William Narmontas that I just mentioned, a lot more was said about Scala. If you use the Scala Collections API, you have a very fluent API in which you can chain higher order functions, and that gives you a very pleasant development experience. And two of those higher order functions are filter and map. Filter, like the name implies, it takes an element predicate and it keeps only those elements for which the predicate holds. Whereas map takes a function, and this function, the map replaces all elements by the result of applying that function. So these are two of the most fundamental higher order functions of the Scala Collections API. Let's look at how they look in Scala. Let's say, well, yaidom has methods such as find all child elements. Well, it finds all child elements like the name implies. Ename stands for expanded name, so it's the combination of a namespace URI and the local part. Now the code below is then very simple, is very easy to follow. We have a variable xbarrel I namespace, which holds the xbarrel instance namespace. We have the contexts, which are defined as follows. We take the root element of the xbarrel instance, we find all the child elements, and then we filter, keeping only those elements that have the name context in the xbarrel I namespace. Now this is very verbose code, but believe me that it can be written far more briefly. We see that filter indeed takes a function. That function takes an element E to the left of the arrow, and to the right of the arrow, or below it, we see the Boolean expression. So that's how you use higher order functions in Scala. The context IDs are defined using the map function. So we map the contexts on the ID attributes of that collection, of those elements. So that's filter and map. Well, if we have seen those, it's also easy to understand the yaidom query API. Many query API methods of yaidom are indeed higher order functions that typically take an element predicate. Most of these higher order functions return a collection of elements. They operate on one element and they return a collection of elements. For example, filter child elements, filter elements or filter descendant or filter elements or self. Well, filter child elements, of course, filters child elements. Filter elements filters descendant elements, and filter elements or self filters descendant or self elements. So the name descendant is left out from the element from the method names. There is shorthand for filter child elements and filter elements or self, which makes them look a little bit more like XPath access. And of course, we recognize 3 XPath access here, but it's not exactly the same because these methods only return elements. They do not return text nodes or processing instructions or what else, just elements. And if you understand these filtering methods, then it's very easy to understand the rest of yaidom. Let's use them. Here we have the instance again. We have 2 namespaces, the xbarrel instance namespace and the link-based namespace. Then we define a function has custom namespace, which takes an element E and returns true if the name of that element is in a namespace other than these 2 namespaces. Then the contexts are defined as follows. We take the root element of the xbarrel instance. We filter all child elements that have the name of context in the xbarrel instance namespace. The units are retrieved in the same way, but are the name as unit instead of context. And the top level facts are retrieved by filtering the child elements of the root element that have a custom namespace. And the nested facts and all facts are retrieved by combining the flat map operation of the Scala Collections API with the filter elums or self operations of yaidom. So the nested facts are retrieved by taking all top level facts, and for each of them filtering the descendant elements that have a custom namespace and then just combining the results into one collection of elements. So the Scala Collections API and the yaidom library, they work nicely together. This of course was still very trivial. Non-trivial queries combine facts with context and units, and then it becomes a bit more attractive to have a language like Scala at our disposal. We define two maps, a map from ID attributes to contexts, and the same for units. And if you have those two maps, then lookups from facts to context and units becomes very fast. So you have predictable performance. So that's the advantage of using a programming language. One thing I forgot to mention is that the code that we just saw here, it works for all the element implementations. So if you plug in your own element implementation into yaidom, you don't have to change anything in this code. Now the second part, the validations. Let's check some commonly known namespaces in the XBRL instance. And let's check that they use their preferred prefixes. And conversely, let's check that these prefixes only map to the expected namespaces. And we assume that all the namespace declarations are only in the root element, which is indeed the case. We see two prefixes that are well known in XBRL. That's the XBRL I prefix and ISO 4217. We see that the XBRL I prefix maps to the XBRL instance namespace, so this is expected. But the ISO 4217 prefix does not map to the correct namespace. So our validation should fail. Now we first check our assumption that all the namespace declarations are only in the root element. So we find all the descendant elements of the XBRL instance root element, and we check that for all of them the in-scope namespaces are the same as those of the root element. Now let's get on to the check. We define a mapping from 5 well-known prefixes to the namespaces. The prefixes are stored in the variable standard prefixes, and the namespaces are stored in standard namespace URIs. Then we define a variable subscope, which is the in-scope namespaces of the root element, but ignoring the default namespace, if any. And then we filter only those prefix namespace pairs for which either the prefix or the namespace URI or both occur in a standard scope. And then the check becomes nothing more than subscope is a subset of standard scope. So it's very easy to write these kinds of checks in Scala. Now this is of course a simple check. It's rather low level, but we have also written far more semantic checks on XBRL, and there we also profit from the fact that we use Scala. The following example checks contexts. We check that all contexts are indeed used by at least one fact, and conversely that all the context refs are not dead links. So first we see in the first code block the same as we saw earlier. So we have some facts, some top-level facts and contexts. And now we just built two sets, one of ID attributes of the contexts and one of the context ref attributes of facts. And we just compare them for equality. That's it. That's the whole check. I don't know how much time I have left. Okay. Okay, so still this was rather simple and rather low level. At EBPI we also profit from the fact that we can build higher level models because Scala is an object-oriented language, so we can wrap lower layers, lower DOM-like trees into high level models and combine those more type-safe trees into models that cross multiple documents. And that gives us a very productive experience for building validations. We also use Saxon a lot for its XML schema type awareness, and we also could bridge those Saxon node info objects to Scala, so we could get the best of both. We could get the schema type awareness of Saxon and the Scala Collections API experience. And yaidom acted only as a bridge between the two. I cannot show now how we can define higher level models. That's too much for a presentation, I think. But to give an idea of what it means for the code that you write for the validations, well, we see here code in which we do not retrieve attributes with specific names or elements with specific names. It's more type safe and it's more expressive. So imagine that you do this on a large code base, that you have the possibility to treat elements just like XML elements, but also as parts of, for instance, an XBRL instance, contexts, scenarios, units, facts. Then we can get the best of both. We can treat them just like low-level XML, and we can also treat them like higher-level, more semantic constructs. So, yaidom is, in a sense, comparable to the standard Scala XML library because it leverages the Scala language and its collections API. One important difference, as we saw, is that we can support multiple element implementations behind the same query API. Well, actually, you can choose how much of the query API you use. A very minimal element implementation is the James Clark element tree abstraction, the labeled element tree abstraction, in which prefixes do not occur, but namespace URIs do. And they're also supported natively by yaidom. They are a basis for checking differences between elements if you don't need schema type awareness. One which we use a lot are yaidom bridges from Scala node info objects to Scala. Like I said, but have not explained, yaidom can also support custom type-safe XML dialect support. And at EBPI, we use Scala, Saxon EE, and yaidom, where yaidom to a large extent is a bridge between the two. And of course, like I said, is that with Scala we can stack layers of abstraction. So that helps in having a choice between writing validations at a higher level of abstraction or a lower level of abstraction. So that was basically my presentation. Are there any questions?
Adam?
You mentioned that it's based or related to the Scala Collections API. Did you actually implement the types behind the Scala Collections API, or did you just implement map, flat map?
No, I used only, I didn't implement parts of the Collections API,
Okay.
not at all.
Okay.
And it's also different because, well, the Scala Collections API mainly transforms collections into other collections, whereas yaidom just takes one element as input, and it typically returns a collection as output. So that's already different. So I didn't try to implement parts of the Scala Collections API. The collections that are heavily used by yaidom have already been chosen. They're vectors, they're index sequences.
Okay. Thank you.
Any other questions for Chris? Okay, thank you very much, Chris.
Sure.